an example, you could do an exercise, example.
I guess we could do 2-5.3. A Gaussian random current has a
Did
probability.
we do this one?
We might have.
No, all right. You shake and say, 2 point what? 2.5 what?
2-5.3.
3, go ahead.
A Gaussian random current has a probability of 0.5.
Well, hold it.
Uh,
This is probability of 0.
0.5 of having a value less than or equal to 1.
Okay, and that means what? The minute they give you that information,
P of-
half the probability is less than, than the mean, right, class? Y'all follow me? So if the probability of having that value is 1/2, or what is it, 1?
The probability of x being less than or equal to 1 is 1/2.
That tells you that the mean is, the mean value is 1. Y'all follow me? It's got 50% chance of being less than 1, 50% chance of being greater than 1. So here, we'll just start, and I'll just put it, I'm gonna use a random variable x. The mean of x is gonna be 1, all right? With me? Go ahead. Standard deviation is 1?
And it also has a probability of x
Okay.
being greater than 5.
And what's that?
0.0228.
All right, this is a classic problem. The standard deviation is buried in the second bit of information, right? Now, on your quiz, I'll provide you tables, but your calculators do this for you. Y'all with me on this? So now when we take a look at this, I've got the mean, I don't have the standard deviation. In general, when you take a look at this, the probability of this function, I'm gonna write the full probability of x right here, being greater than or equal to any small value of x, is an integral from minus infinity to x of 1 over square root of 2 pi. And then the standard deviation appears, exp to the minus, and here it's going to be x minus the mean value, right? It's actually, don't need the capital, squared over 2 sigma squared dx. Now, I should probably put u, and u, because we're going to integrate this out, and u. I don't want to confuse you, because that's going to have a function. What we call this thing is it's really he calls it the distribution function, but this is the integral from minus infinity to that point. So in his book, he uses, I think, f of x. That's a common notation. Capital F usually means cumulative. Small f is density, probability density. Once we have that, we know the value of this, f of x, when x is equal to something we're going to calculate, we don't know this, is equal to 0.0228. So on your tables, I told you I'd provide you with the cumulative distribution function. I could have provided you the q function, right, which is 1 minus the cumulative. You all with me on this, class? So I provide you the cumulative. If you look in your book, or if you have a calculator, your calculator will do this. It'll do the reverse q note. What we're going to do is say this. I know that f of x equals whatever here, is really equal to the normalized, and here he uses this symbol in the book, I think, or actually I think it's this, it's this capital, right? I think. And now you have to normalize this. So this is x minus x bar over sigma x, and that is equal to 0.0228. If y'all with me on this, class? This is normalized, correct, class? This is normalized, and it is the, whatever he calls it, the characteristic function. It's just the integration from minus infinity to there, but it's normalized, right? So this, we can just say, I'll call this, let A be equal to x minus x hat over sigma x right here. And now if in your tables, remember, x for this one is 5. Oh, I'm sorry. He says the probability of x being greater than 5 is this. So what we actually have is this. I'm sorry. Let me erase this. I'm trying to get through this kind of fast, but let me explain this better. So if the probability of x is greater than 5 is this, and this distribution function is from minus infinity to x, what we really want is, right here, we want the probability of x being less than or equal to 5, which would be 1 minus 0.0228. Do you all agree? I'm gonna stop trying to race through this and just get to the point. Everybody with me, class? So this right here would correspond to this information right here. So I'm gonna have the probability of x less than or equal to 5 is equal to, and that's going to be this normalized characteristic function of x in this case, I should do it this way, is 5 minus the mean of 1 over sigma x, and that's equal to 0.0228, right? Now what I'm really doing is, you think about this, if we have a standard Gaussian distribution right here, and this is f of x, this is x, right here. This is the mean value, and our mean value was 1. We ascertained that from the discussion in the early part of the problem. He says for a value of x greater than 5, this area under that curve is 0.0228. Now he just states that explicitly. So you can use tables or you can use your calculator to get this, but you have to do the normalization. So the probability of x being less than, and I did this wrong again, it's 1 minus the characteristic function right here of, let me do it here. This is 1 minus the characteristic function of x, which is 5, minus the mean, which is 1 over sigma x, right? Or I'm going to call this 1 minus the characteristic function of 5 minus 1 is 4 over sigma x. Or 1 minus the characteristic function of a. Here, a is simply equal to 4 over sigma x. I spent a lot of trying to get this through this too fast. But y'all follow me, we're after this area. If we use the Q function, we don't have to take 1 minus it, but we're using the characteristic function of the cumulative distribution function. Y'all with me? Okay, so look in your tables. If I take a look at this,
The probability is equal to 0.977.
okay, so that means what we want is the normalized characteristic function of A, that's the argument we want, is 0.997, right? All right, if you look in the tables, what do you get? You can use your calculator to do this, by the way.
I'm trying to figure that out.
It's just a reverse search. Look at Q norm, and that is a standard notation. Or, yeah, Q norm should do it, I think. See it?
I see an inverse one.
That's the one.
Area, area.
Your calculators have this. I promise you. Has anybody tried to do this on your calculator? It'll give you the inverse value. I did this on, well, I used some of the computer tools, MathCAD and stuff to get the inverse. But this is a standard thing. So what do you get for this if you use the tables for A?
It's 2.
What?
2.
Just 2? Yeah, it is, I think. So what is 2? It's that argument right here. Y'all follow me? Take a moment, just think through it, what I'm doing. I'm given this information. Actually, it corresponds to the area above here. Well, that area above here is 1 minus all this area, right? That's the reason I use the cumulative distribution function. Do you all agree with that? Well, once I have the cumulative distribution function here, I take the 1 to the other side, and now this is the normalized value right here. You all with me? Just take a moment. You all follow me on this, class? Do you follow me, sir? You're looking at me like, yeah, you. You, yeah. You with me? You don't? What
Where
don't?
exactly did you get the .997 from?
All right, when we had this information right here, that's this area, right?
Yeah.
All right, we don't want to use the Q function. We're using the characteristic function. So we need 1 minus that area. That's right here. That is 0.997 about, right?
Oh, okay, yeah.
That's what, so now we're using the characteristic function. That's this from here all the way up. So we look in the tables and we say, what is this argument here, right? And once we have that argument, we find it's 2. Can everybody find that, by the way, in the tables?
How do you find that in the table?
It's the character, we're using the characteristic, not Q, remember? Yeah.
Shouldn't it be 0.977?
It's 0.9772,
Yeah.
which equals 2.
Okay. It's a 979, I'm sorry, 997.
Or 9, it's
Is
0.
it-
It's 0.9772. Yeah.
All right, you got me on, it's about one, I think it's 1.999 when I get it. All right, I got 1.9. Y'all with me, class?
You're like
Does anybody not, you good with this in the back, far back?
772. It's 2.
What don't you understand? If I can help you, if you can tell me where the disconnect is. Mainly, it's just seeing this. If you can see, you understand, he gives you that area, right? What is that area? It's 1 minus this area, right? What is 1 minus, what does we call it? That's the distribution function, right? So the normalized distribution function is what we'd use, right? Can you all follow me? Can you see that now? In the far back? Or not?
I put it in my calculator.
What, sorry?
Get a negative number when I put it in my calculator.
No, you can't get a negative, you can't have a negative value there. All right? If it would be less than, that would be a probability. If the mean is 1, a negative value of the argument gave you that. Oh, I know what you're doing. You're doing this area. You're going down here, I think. I think. Did you set it equal to 0.0, whatever that is, 228 or something?
I did the inverse norm of 0.028.
No, this. Do that. That's the bet. It's 1 minus that. I'm sorry, I misled you.
Oh,
in the
it's
beginning.
772. 0.9772.
Yeah, 0.9772. Pardon me.
Now it's correct.
Huh?
Now it's correct.
Now it's correct. Okay. Now it's. You all follow me? And you can use your calculators and tables. I'll provide you the characteristics, the tables for the integration from minus infinity to x of the normalized value, the characteristic function. You got me, class? I sent them to you. But y'all see that email? Okay. All right. Now,
So what is A?
I'm about to get there. All right. Now, that's the argument in the table, right?
What's labeled Z? Z
I don't care. ZA, who cares? It's a value right there, right? It's the argument that gives the characteristic function a value of 0.9772. That's the whole deal. Can you all see that? Now, if you look at that, what is A? A is this, right? Because that's unnormalized. Correct, class? So that's equal to 4 over sigma x. That means sigma x is equal to 2. Now, coincidentally, both this A value and the sigma is the same. But obviously, you got to set this value, which he calls Z in the table, because he has Z variation down. He calls Z equal, it would be equal to 4 over sigma x. If this was a different number, whatever it is, you just divide 4 by that and put sigma x over there. Yeah.
I guess we can finish this. But
I'm sorry?
I know. I'll just ask you.
You all with me on this? You have to be familiar with the terminology and what they're really talking about. Think about area under curve always. All right, so what's the next part?
Find the probability that the random variable has a value less than or equal to 3.
Now, what are we going to, I'm going to do this over here. So we've got the standard deviation, right? Go with me. We got the standard deviation is 2, and I'll put it here. For this problem, we have the standard deviation and the mean. So here we have the mean of x, I'm going to use x, is just 1. The standard deviation is equal to 2, right? By the way, you can write a function to do this, by the way. I did this with MathCAD. I'm sure your calculators will do this, but you really have it embedded. It's programmed into almost all modern calculators. So, and I think you can put in, now we're going for we're not doing a reverse, we're doing the forward search for the probability. And he wants the probability of what? X being what now?
And then you say
Say again?
Find the probability that a random variable has a value less than or equal to 3. X is less than.
All right. Now we're doing the forward, not reverse. So for this one, we've got the characteristic function. So we take a look at this. The probability of x less than or equal to 3 is the same thing as a distribution function of x equal to 3. You all follow me on that? Because now we're using that. What is that? Well, that's the characteristic function, because the characteristic function would be the normalized value of this. Can you all follow me on this, class? How many can? Raise your hands. Can you follow me back there or no? Far back. Okay, you got it? All right, so here, it's the characteristic function of x minus x bar over sigma x. Now we've got x bar and sigma x, right? We need, just put in this, we say now that's the normalized value of x, 3 minus the mean 1 over sigma x, which is 2. He picked nice numbers. So that's phi of what? Minus, 3 minus 1 is 2. 2 over 2 is minus 1, right? You all follow me? Now, if it's a negative value, you can look up the negative value in the tables I provided. They have that.
It's
But, huh?
It's 1.
What? Oh, I'm sorry, 1 plus 1. Sorry. Man, 2. Plus 1. If it was negative 1, you take 1 minus that. But anyway, if it's plus 1, look at your tables or use your calculators. Please try to do this. Regardless if you're using tables or calculators, you're going to use your calc, aren't you? All right. What do you get for this? For this value?
0.84.
Yep. 0.84. It should be 3 digits. 8413?
Yes.
Okay. Does that coincide with that?
Oh, well.
I'm pretty sure it does.
Yeah.
All right? It does. All right, y'all with me? Now, if you got calculators, you want to do this, make sure you can do this and not make mistakes.
Does anybody know how to do the first part with your calculator?
How many do? How many? You got an Inspire, right? How many have an Inspire?
Do you need it?
Does anybody need help with an Inspire? You do? You need help? Can you show him? Just go. Take. Don't worry about that.
That problem's finished. Can we do one where the mean, we don't know the mean?
How about you got one for me? I can make one up, but it's easier to just, you got one? All right. So here, now remember, let's do it, I got one for you, all right? Here's a good one. Remember, we didn't do this, but what is the third central moment of this distribution?
0.
Class, what is the third central moment?
0.
What is the fifth central moment?
0.
What is the seventh central moment?
0.
All right, you got me on that? I'm trying to ingrain that in you. All right, now, if they're even, you don't do that. You got me on that? If they're even, you have to go through the formal calculus.
Is it, if it's even, could you do the central movement? Could you do the odd factorial thing where it's like 1 times?
No, for a Gaussian distribution, all right, if it's an even, right? Remember how it says 1 times 3 times 5, times n minus 1 times sigma to the nth power. You remember that? What was that?
That's the central.
What?
That's the central limit.
Of even functions. Of even functions, right? Yeah. For even, you can do that. All right? You're looking at me like it sounds suspiciously wrong. No.
Is that the even function?
Well, this is a density function, right? Hear me, class. Remember, this is a density function. The f of x, if you wanted, is what? This would be f of x, right? If I just got rid of that integration, that is f. I gotta put f of u. It's a function of u here. You all with me? That is what's called the normal distribution function with the mean. It's not normalized here. It's the Gaussian distribution or Gaussian density function without normalization. With normalization, that goes to 1. The mean goes to 0, right? And it collapses. You're with me? But for that one, you're asking about, now what about moments, right? All right, so if you wanted a moment generating function, I was playing with this the other day. So a moment is really the expected value, let me do it this way, the expected value of x to the nth. You all follow me? Yeah. X is the random variable to the nth power. We're gonna get this. So what is it? Anytime you have an expected value of anything, it doesn't matter what that function is. It's just going to be an integral from minus infinity to infinity of that function. Here it's x to the n times the density function, which would be f of x dx. I can leave x in there because the integration goes to infinity. Now that is the moment. Anytime n, right, this is just the moment. This will not be 0 for, I mean, it can be. Generally speaking, it's not 0 for even or odd. That is the moment, not central moment. Y'all hear me? That's the moment. When we talk about central moments, we're talking about the expected value of the function, of x minus the mean. Now you gotta subtract out the mean to the end. And what that is, the same integration, but now it's gonna be x minus the mean to the nth power times f of x dx. Here the f of x is the f of u here, replace u with x. Got me on that?
What's the difference between those two? You said one was the central moment and then the.
Well, look, this is just x, right? This is x minus the mean. Here we're subtracting the mean, right? So when you hit the mean, this is 0, isn't it? And below the mean, if this is an odd function, if x minus x bar right here is an odd function, then the area below is same as area above, because it's at the mean now, remember that. But it's negative in terms of its sense. So it cancels, it goes to 0. Anytime n is odd there, it's 0. 1, 3, 5, 7, 9. However, when it's even, it isn't. You got me? If it was just, if you wanted this value, the expected value of x squared, well, that would be for a normal distribution, or for any distribution, it would be a standard deviation squared plus the mean value squared. Y'all with me? That's second, but for third and fourth and fifth moments, you don't know. You've got to put this, if it was n equals 3, you got to expand it, right? And then you have to replace, I'll just do this one time. Do it here, and I'm trying to give you an appreciation for how I view this, how it really isn't that hard. The problem a lot of times is terminology and you have to get a visual, I have to get a visual idea of what's going on. So if you take a look at this, remember central moments always subtract off the mean from the variable and then take it to the nth power. So if we had the third central moment, the expected value of, say, x minus x bar cubed. What I do right away, before I do anything, I'm gonna take this and expand it, okay? So if you get x minus x bar squared, that's equal to what? It's x squared, right? Then it's gonna be minus 2x bar times x, and then it's gonna be plus x bar squared. You don't have to write this down, but you all with me on this, right? Now if you take this and you multiply it by x minus x bar again, because that's cubed, you all agree. When you do it, what do you get? Down here, this whole expression is multiplied by x, so you get x cubed minus 2x bar x squared, and then it's going to be plus x bar squared. I wish I used a instead of x bar. Then I have to subtract. I take this and I multiply this right here, the negative x, and multiply that. So I get minus right here, and it's x squared x bar. Then it's going to be plus 2x x bar squared. That's this times this, right? This times this is going to be minus x bar cubed. Can you all follow me? I want the expected value of this. Just watch this. I was messing with this. It gets a little irritatingly long for fourth power and stuff like this, but after a while, you get used to it and you sort of even recall the generating function for this. If you take a look at this, this itself is really what? Remember, it's the expected value of x minus x bar cubed, right? And that equals, first one is the expected value of x cubed, and then it's going to be minus 2, remember x bar is a constant, and then it's the expected value of x squared. Can you follow me? I'll just stop for a second. You see how that's x squared there, right? X bar is a constant. So the expected value of x squared is what? Standard deviation squared plus mean squared. You all agree with that? Everybody? I'm going to put it in here. And I'm just going to put x bar squared plus standard deviation, just sigma x squared, right there. It's minus that. Then it's this. X bar, now look, expected value of x bar squared, that's a constant taken up. What's the expected value of x, class? X bar, right? The expected value of x is just, it's labeled x bar. So the expected value of x squared is sigma x squared plus x bar squared, correct? Okay, so what I'm trying to do is show you how I would do these things, kind of do them a little faster than this, hopefully without making mistakes. So I've got this right here. Now what about this one? You tell me what it is. Now, isn't that right here? X bar squared is a constant, right? Expected value of x is x bar. So this is x bar cubed, isn't it? Class? Y'all follow me on this one? Right here, if you just focus on this. The expected value of that x bar squared is a constant. Take it out in front. The expected value of x bar. X bar times x bar squared is x bar cubed. Keep going. What about this one? You know what I should have done is actually simplify this first. That would be, but that's okay. So it's going to be what? X bar, it's going to be minus x bar times what? Sigma x squared. The expected value of x squared is?
X bar squared plus.
Right, x bar squared plus really the variance, right? And then finally, what about this one? It's going to be 2, and this is going to be what? That x squared is a constant.
X
2
bar
times
cubed.
2 x bar squared is 2 x bar cubed, right? So it's plus 2 x bar cubed. And finally, the last one is just minus x bar squared. The expected value of the constant is so minus x bar cubed. Now, you can see we can condense all this down. I could have done it here, and I should have probably. Do y'all agree with that, class? What happens? Well, the highest power right here is x cubed, right? We have to, I'll just leave that as the expected value of x cubed right here. Now, all this other stuff, these are known values. Now, let's see. We got x bar cubed. I can factor this out, but you all see you could factor that whole mess out and you can cancel. But everything over here is known. You all follow me? So this is the only thing not known. What's this all equal to? 0, right? That's a central moment, third power. It's 0, right? So take this to the other side and you can solve for it. Y'all follow me? Without doing integration. Y'all with me?
And the first moment is basically the average.
First moment is just what? The average or mean value, right? The expected value of x or x bar, correct, class? Y'all see this? I just wanted to write it down, and I'm sorry I did. Yeah.
So for the fourth moment, since it's not equal to 0, you have to FOIL it and multiply it.
The fourth moment itself, you're gonna have to calculate. All right. And the nice thing about this is, in your calculators, I'll get to this later, in your calculators, they literally have, and yours does too, you can put the function you want the expected value. I think you can on yours. I better be careful. I mean, if it's just of the form of x to the nth, you could put in expected value, x squared, where you enter also the standard deviation and mean. I think in your calculators, I'm almost positive they all do this, but again, I don't.
I tried to do the integral part, but I kept getting it wrong.
Yeah, it cannot be integrated.
No, this is a numerically integrated term. You're talking about this one?
Not that one. Well, technically,
Yeah, but
you were using
using a
that.
definition of normal distribution.
You can get the central moments, can't you, on your calculator? It's not a formal integration, it's a lookup on your calculator, I think. Let's not worry about that right now, but I do want to encourage you to these problems, all these problems I've given, try to find a way to do it in your calculator. And I found out almost all the modern calculators do everything I'm doing with tables, that's available to you. The reverse search as well as the forward search. Yo, how many tried to do this stuff on your calculator? Your calculator is the easy way. Once you get, I mean, it's no brainer. You don't have to go down tables and try to squint and figure out. what the value is. Okay, that's that problem. You asked for a problem with mean?
However, the mean is different.
Okay, I'm gonna make one up, guys. There probably is one in the book, but in that book, the first book, this thick, I'm sure there's plenty of problems in it. This book is a lot. Okay, so I'm gonna make this one up, and I'm gonna slow down. Is anybody here had Dr. Nelson? Vic Nelson? What's the one feature of listening to a lecture by him? Fast. Man, that dude talks at 2x my speech. I'm trying to tell myself mentally right now, slow down. Generally speaking, when people start talking fast, people get excited. Something's wrong. Okay, I'm making up a problem. Got me? Here we don't know the mean. So I'm going to say that the standard deviation for this one is equal to 3.
Oh, so you have to basically know one of them.
You got to know something, right? If you don't know anything, you don't know what to do. So I got to give you either the mean or the standard deviation, right? Here, I'm giving you the mean. Got me? Now, I'm going to say the probability, and this is a random variable x, right? And I'm going to say the
You mean you're giving us the standard deviation?
I'm sorry, standard deviation. I'm looking for the mean. All right, I'm sorry about that. I'm trying to calm down. I'm gonna have to tone down the amount of caffeine. All right, you with me, class? I'm looking for I'm gonna give you the probability of x being greater than 4 is equal to 0.125 or 1/8, all right? So now I want you to tell me the mean. I encourage you to try to get a mental picture. So what am I actually giving you? Think about a normal distribution. The mean's out here, we don't know what it is, but now I've given you this. I've said that's the, I've given you this kind of information. We don't know what the mean is, but we know when x is 4, this is with x, that the area under here is going to be 0.125. We know that area right here. Follow me? I could write the description for this down mathematically, but I think you see it by this time. Is everybody good with this? So what is that really? Well,
1/8?
Huh?
1/8?
No, I mean, it is 1/8, but what I'm really getting at, if I'm going to use the cumulative distribution function, that's 1 minus the Q function, I want the area down here is what I want to talk about, or what I want to look for information about. So I'm going to say, well, that area down there in blue is really 1 minus 0.125, or it's 7/8, right? Agree, class? Just leave it like that for now. Everybody with me? Now, to that end, the next thing I'm going to do is say, now the probability of x being less than or equal to 4 is 1 minus 0.125, and this is f of x equals 4. You all follow me? Making sure everybody can see it. With me? So now I'm going to take that and I'm going to turn it in or equate it to the normalized distribution function, okay? So for the normalized, and this is the distribution function, and I'm using this symbol, it's normalized. So that is x, which is 4, minus the mean, which we don't know, right? Over the standard deviation, which I gave you is 3. You all follow me? Do this one in your calculator with that inverse. And that's equal to 1, or this is 7/8, isn't it? Whatever that value is, you can give it to me numerically because we're going to need it.
0.875.
0.875. That's the value of what? It's really the value of the characteristic function, and I'm just using, we can use z if you want. And z here is equal to 4 minus x bar over 3. Now, that's in the table, isn't it?
I-
Hold on, this is this characteristic function. Okay. So this is equal to 0.875. And what value of z corresponds to that in the table, or from your calculator?
I think it's 1.15.
Take it in your calculator.
I'm having a hard time figuring out how I would
Oh.
put that, because it wants you to put the mean.
No. You gotta get the inverse, right?
Like, I'm on inverse.
Inverse will give you the value of x, right? That's normalized though. Yours is normalized, so that value right here, oh boy. I messed with this like yesterday. When you do an inverse, if it's a Q normal, it's already normalized, right? You're getting this value of z. When you take the inverse of this, you can't put in, if it's a normalized function, you don't have a mean or a standard deviation, it's normalized to it.
It's different.
Does it? Hold on for a second. Look at your tables if you don't know how to do it with your calculators, but you'll learn to do it with your calculator. Does anybody know how to do it in your calculator? What did you get?
For the answer?
For the value of z right here. Huh? Say again? Somebody? Who's saying it? That's all right. Who knows? Say it again? Who's talking? 1.1? Is that right?
That's correct. Oh, 1.15.
All right. 1.15, that's the value of z. That's the value of the normalized variable right here, right? That corresponds to that area, right here. Can you all follow me? How many see this? Now what is the z? Now I have it over here. I have z, which is equal to 1.15 is equal to 4 minus the mean that we're looking for over the standard deviation is 3. So to get the value of x, I take 1.15 times 3, right? I've got that. Now I've got to take 4 to the other side, so it's minus 4 is equal to x bar. And again, I'm just rearranging this right here. Do y'all follow me what I'm doing? All right, now, since that's minus x actually right here, flip the signs, I get 4 minus 1.15 times 3 is equal to x bar. You asked for it, so what is it?
0.55.
0. What?
55.
Is that right? 0.55. All right. Now we've got the mean. But the real key is this. Once we have this normalized distribution function's value, the normalized, we're just after this value. I call it z. So you're doing the inverse. Once you have that, you've got if you have the standard deviation, the value right here that I tell you that's where the value of the probability is greater than that or less than, then you can get that. Does that make sense? How many see how it works? Go ahead.
What if you gave, in the problem statement, what if you said the probability of the
Event.
event is less than or equal to 4? Do we just use
Less than or equal to what?
less, like if you didn't have to, is there any case you don't have to subtract? from one?
Yeah, sure, we can do that one. It's real quick too. Just listen to me. I gotta make sure I slow down. All right, suppose this is the case, class. Just talk to me now. All right. Now we're after this area, aren't we? Right? That is a distribution function from minus infinity to point x, right? We're going to normalize it, right? So we're going to say what we want is the probability of x right here less than 4 is the same thing as what? The or the distribution function here of, this is normalized, of, and here, x goes here, right? It's x minus x bar over sigma. So x is 4 minus x bar, and x bar, I'm assuming we know it. What was x bar?
We know the standard
Point,
deviation.
yeah, but what is that, 0.55?
Yes, sir.
0.55 over the standard deviation, and I gave you 3, right? Just do it with me, all right? You asked for it, I'm gonna give it to you. All right? So, by the way, this should be what? 1 minus what we just found. I mean, the calculation. So what is this value gonna be? Characteristic function of, what is that? 3.45, right? Over 3. So So that's the characteristics functions of, I don't know what that is, a little greater than 1 point something. What did you get for 3.45 over 3? Say? 1.95?
1.15.
1.5, yeah. 1.15. So look that up and tell me what the value is. This is direct. Now you're going down the values of z. You find 1.15, give me that value. 0.8749? Now you can do that in the calculus. That I guarantee. Did you get that?
As you saw the function.
I'm trying to make sure you guys see this. I'm giving everybody a chance. You got it? Not on your calculator? The reason I'm telling you to learn how to use your calculator is because I found this in the last couple of days messing with it. It does all the stuff we're doing seamlessly. It's quick. I want the second moment, third moment. I put in the functional form. The density function is predefined just by the mean standard deviation. Go ahead and do it, bang, it comes out. And it's not even, I don't have to do all that multiplication crap I did up there. It just whips the sucker out. Okay, now, I would like to cover, do you have any other questions? Because I know everybody, anytime there's a quiz, people could care less about other stuff. They want, how do we do the quiz? That's the focus, and that's understandable. I need to cover some stuff. This is in the next section I gave you in this book, Cooper and McGillen, because it's in this book too, but this one kind of does it in a way that's more understandable, with less complexity. If you found this book to be kind of complex with some of the problems, some of them are bizarre. I mean, the Merlot, Zinfandel, and Cab problem, they didn't need to use 8, 10, and 12 to get the point across. They could have reduced that. But and some of the other problems I looked in there, I'm thinking, I'm going to spend 20 minutes just on routine calculations to see the point. You don't need to do that. So I got a few things I want to do. This is in the section, just let me do this and you get the quiz. Give me a break, and I'll try to thumb down the caffeine. I'm sorry. Okay, so now he's talking about other distribution functions. The most common other distribution function you run into all the time is one we used already. It's the normal distribution. I'm sorry, the constant distribution. So if they say that f of x, this is the probability density function. If they say it's equal to a constant, c, I'm giving it to you. And the value of this, now I'm going to draw the density function. This is going to be my f of x, and it's going to go from some x1 to some x2. And this is in that book. And then here we're assuming x2 greater than x1. So this is what it looks like. It's just a constant. This is the value c, right? Now that's a probability density function. How do you calculate c? Just tell me in your own words. Anybody? What's the one property you know, right? Exactly. The integral from minus infinity to infinity of f of x dx has to be 1. The area under that curve has to be 1. Do you agree with that?
Yeah.
It's a rectangle. Width, right here, is x1, or x2 minus x1. That means this height, or the c value, is 1 over x2 minus x1. It's almost boringly simple, right? Now when you take a look at that, the next thing you need is the expected value. So what's the expected value of x, or the mean value, I should say? It is the mean value. How do you get that? Just do it forward integration. It's a constant. It can't be that tough, all right? So what is this going to be? Well, that's equal to the integral from x1 to x2 of whatever this function is. In this case, it's x, times the density function. Well, the density function is a constant. It's c dx, right? We've showed the values. You all with me? So what's the integral of x dx? It's equal to x squared over 2, correct? Evaluated from x1 to x2. Now I'm going to put in the value of c here. So that's 1 over x2 minus x1. And I'll put the half here, 2. And now I have what? Upper one is x2 squared minus x1 squared. Do you agree with that? So how can I rewrite that top one? It's 1 over 2 x2 minus x1 here, isn't this x2 minus x1 times x2 plus x1? Take a look. Just for a second, convince yourself I'm not messing up. Y'all follow me? How many see this? So what cancels? It's obvious.
X2 minus X1.
That's right. And that means the expected value for a constant distribution, the expected value of x is simply equal to 1/2 x2, right, plus x1. Now that kind of makes sense. It's the average value of the extremes. With me on that, class? Now the second moment is a little trickier, but I'm going to give it to you. I'm going to give you the second central moment, then we'll get the second moment. By the way, you can do this numerically. So how would I get this expected value, now that I've got the mean, of x minus x bar squared? Remember, I have the mean. I can do it formally, right? It would be what? It would be the integral from x2 to x1 of the probability density function, which is just going to be 1 over x2 minus x1. I should probably have left that as c here. That's all right. Right, that's the probability density function. Now I need this in here. So it's going to be x minus x bar squared dx. Now, does everybody agree with that? You can take this out in front. That's it.
Why are the bounds flipped?
Because I made a mistake. That's my bad. Everybody with me on this? When you look at this, really, this is a distance. If we think about this for a second, just for a second, take a look at this. When we look at x minus x squared, here's the mean value, or I mean x minus x bar squared. Here's x bar, right? This is x1, this is x2. How many see the distance above is the same as distance below the mean? You all with me on that? Now, the way I did this, you can do it a couple of ways. The way I did this, I played with this. When I look from here to here, if I could calculate and integrate the value of x, because that's a center moment, if I could just do this, I'll put it down here. Take the probability of, or the constant value, x2 minus x1 out. And now, if I take this right here, and I say, since the area, if I look at this right here, I know when I do the integral from here to here, it will have the same areas from here to here. It's a square, I mean, of x minus x bar squared. Do you all agree with that, class? So what I'm going to do is say, I'm going to do this, I'm going to say it's really 2 times the area, and now I do something even better. Since I'm really talking about x bar minus x squared, I can look at this thing as this. I can, because right here it's 0. Do you agree with that? X minus x bar is 0. I can go from 0 to, and this would be simply x2 right here. Now it'd be a different distance here. x2 minus x1 over 2. I'll tell you what I'm doing. I know the distance from here to here is x2 minus x1, right? Half that distance would be x2 minus x1 over 2. That's the distance from here to here. Does everybody agree with that? Now my integration is going to start at 0 because I know x bar minus x here would be 0 when you're at x bar, when x is x bar. You all agree with that? So I'm going to take that and I'm going to integrate it. Where am I doing that? Right here. I'm going to take twice the integral from here to here of, and now it becomes simply x squared, and this is a dummy variable, but now I'm going to take this x minus x bar, call it x squared, or maybe I should find a different variable. I'll just call this y equals x minus x bar, right here. And I take y squared here, it would be dy, and it goes from here, or 0, to the upper point, or x2 minus x1 over 2. You don't have to do it this way. I found this to be easier to understand. Now, take out the front 1 over 2, or 1 over that 2 over x2 minus x1 here. The integral of y squared is y cubed over 3, so it becomes 1/3. And y cubed evaluated top to bottom, well, the bottom is 0 on purpose. So it's really going to be x2 minus x1 over 2 cubed, and that would be the expected value of x minus x bar squared. I want you to just focus on what I've done. Now, the only thing you have to do is evaluate this integral any way you want to. You could do it numerically. If you had actual values, you could just do it, actually do the integration. Do it numerically if you had the actual values of x1, x2, and x bar, or you can do it symbolically. And if you do it symbolically, you'll notice this is what you get. So what is that expected value? Take a look. Well, here, just follow me on this. I have 2 over x2 minus x1. Then I have 1/3. All right, now 1/3 here, but I have 1 over 1/2 cubed, which is 1/8. Do you agree with that, class? You all with me on what I did? I got 1/8 and I got 1/3 here. I better put the 1/3 back in or I'll mess up. So I have this. When I take care of the 1/3, take the 1/2 cubed is 1/8. There's a 2 here. Now, if you look at this, x2 minus x1 cubed, can you all see that one of these cancels? So now I have x2 minus x1 squared. What is that? That's x2 squared, and then you get what? Take a look. Do y'all agree with it? It's x2 squared?
Minus 2x2, x1.
Minus 2x2, x1, and it's going to be plus x1 squared, right? Agreed? And I cancel that. That factors, doesn't it? And let's see what we get here. We got 3/24, so you get 1/12, right? And that becomes simply what? x2 minus x1 squared. And he'll call x2 minus x1 delta in the book. So this is really the delta, or the difference in the two, squared divided by 12. Now, I am not going to have time to get where I'd like to go because I think I almost overstated. Do you guys have time for a quiz now? It goes to 11, right? All right, you do. All right, so could you do me a favor? Could you fill up the first row? Everybody in this row, just move over there.